Okay, okay.
Not mistake exactly, but I'll share it.
Which one?
It was like very I'll show you. So I am this kinematics 2-1 May.
Huh.
I'll show you. I have saved it somewhere, but I just in the PDF I will show you like in a couple of minutes. So, yeah, of
Sure, sure.
course it's not a mistake. It's just sign problem, but it's like he has to mention that. But like okay, are you recording it? Okay, I will not say anything controversial. Yeah,
No, we'll come to that. We'll come to that. Yeah, we'll come to that. Yeah.
because the issue is, Professor, like you have much, like you have super command on the subject. Actually, it's like you have super command.
Okay.
You're not like you're following
Yeah, please
something.
do let me know. We'll discuss that. We'll discuss that also. Yeah. Yeah.
So lecture notes. Exactly.
Yeah.
How long does it take to open this?
Which particular notes? I mean, I actually have printed entire.
Oh, printed.
Yeah, what I do is I take 8 slides on one sheet of paper. Otherwise, there will be too
Yeah,
many
yeah.
paper sheets,
Actually,
right?
it's yeah.
Yeah, yeah.
So I have just
So,
opened some sheets, and I think I'm not sure if I can find it now. Yeah, this is all okay. So at one place, he's doing this dx and dx1. Can't find it now. Is this previous?
okay.
I wrote the notes also, but I will check that. I have the notes. No, it is here only. Sorry, free form. So here, yeah.
Okay.
Mm, okay, I can't find it now, but
Okay. Please, yeah, please do let me know. We'll try to, yeah.
I think I will just I can see and I will tell you. Okay, it's
Sure,
okay.
sure,
But
sure. Yeah.
it's just that at some point he has to do D. So he says X1 and 2, but it has to be P and Q. It's not
Hmm.
just that. It's not just P. It's not just variables. It's a
Hmm.
bit more
Hmm.
deeper than that. It's like he has to consider some. The way he should say is should be very different.
Hmm.
Anyways, okay, let's fine. Just keep going. So in the
Okay.
lecture notes, there's so many mistakes. So while he's teaching, he's correcting the lecture notes. He
Yeah,
says this is
yeah,
correct, this is wrong.
yeah.
He does that.
And in the final, actually, in the final slides, almost all the, I think, mistakes are corrected, I believe.
Oh, is it? Okay.
Because to what I see, yeah, yeah, yeah. In the lecture notes, in these notes, the final ones which are uploaded, I see that there are no mistakes anymore.
Okay,
So
that's
whatever
fantastic.
mistakes the professor corrected there. Actually, I think the professor went through the slides and actually corrected and then uploaded. So there is the, yeah. So yeah, there is no need to worry about that. Yeah, because I also had that issue, and I said, okay, all the mistakes are corrected here. It seems.
Good,
Yeah.
great.
And the thing is
Okay,
that
we'll start.
helps us also. Otherwise,
Yeah.
we cannot. Yeah, we cannot because these are more to our with. I mean, for our reference purposes, right? All these notes, and these are very good set of notes also in a very what do you call very compact form as well as
Combat
in
form.
a much yeah comprehensive form. Yes. So what I'll do is I'll just switch off the camera. Actually, this actually I saw that it takes a
Good.
lot of bandwidth.
Yeah, yeah, of course, of course. Yeah.
Yeah. Yeah. So what we'll do is, I mean, for today, what we are planning is just isotropic hyperelasticity and compressible neo-Hookean material. but we will start from what we wanted.
Okay.
We will actually will. The thing is, it's better to continue with what we were doing, so that it will complete the picture, right? So we had wanted to start with the principle of virtual work, isn't it? So it was principle of virtual work. I hope things are visible, right?
Yeah.
Okay. So we'll start with principle of virtual work.
So we will switch on video if you want to discuss something like, like with hands or something.
Yeah. So in principle of virtual work, the thing is, why do we need principle of virtual work? At least in the context that we are discussing here. The thing is, when we discuss about all these balance laws, right? Balance laws, we saw that balance laws were all in differential form.
Mhm.
And the good thing with of differential form is that they tend to satisfy all those conditions at every point. Actually, I mean, as the something like at the material point level. That is the good thing. The bad thing is we cannot find solutions to such problems, because we ultimately we need to determine numerical solutions, isn't it? So we cannot determine numerical solutions, uh, what you call, by satisfying such point-wise conditions. Like this, the thing is, when we write all the equations in differential form, right? Say when we have rho dot plus rho divergence of v is equal to 0, this has to be satisfied for every x is an element of the body at parameterized at t.
Okay.
So it means that when we take a body here, so it has to satisfy at every material point. It has to be satisfied at every material point, this relation, this particular relation. And you know how cumbersome it is, right? To satisfy something at every point.
Yeah.
Isn't it? So all the laws have to be satisfied at every point, and which is something called as a very strong condition. So, and although this is mathematically very rigorous, in the sense that if we can actually determine the solution of a differential equation, that is the actual, I mean, that's the best solution we can have. However, it's not possible, isn't it, to satisfy at every point. So what we do is we try to satisfy these relations, satisfy the balance equations in something known as in an average sense over the entire domain. Now let's talk about what do we mean by average sense. Average sense means it's more like at fewer points, at what we call at finite number of points. And this is something called as a weak condition or a weaker condition. And let's try to understand why this is the case. So say we have a domain here, right? We have a domain here which parameterized with t means some time t, and we want to satisfy equations, balance equations. Say we'll just call it L as operator of u is equal to 0. At every point, this has to be satisfied. However, the other way is we have the same body. Okay, let me try to replicate as much as I can. Yeah, we have the same body. However, what we do this time is let's have the same balance law. And before we were asked to have this 0, so it was like strong condition. Now what we do is let me use x actually to determine that things are with respect to x. X means our Poisson vector, and we can have like this is a linear operator, isn't it? So we can have double derivative, all that. So L can signify d square by dt square plus something, and then all that. So it's just a compact way of writing things. Now what we this was a strong condition. Now the other what we do is let's make it slightly weaker in the sense that let's have let's first multiply on both sides by some w. Okay, some vector, some w, and then and here, yeah, some w we call it, or delta w, let's say. And then when we multiply with 0, it will still remain the same. It's just 0. And then what we do is let us integrate it over the domain. So let's integrate it over the domain. This is bt. So with 0, even if you multiply it, integrate over the domain, it will still be 0. So what we saw is we started with a strong condition, multiplied with some function, and then integrated over the domain, and it will still remain 0 on the right hand side. So what we see is,
Yeah.
yeah, sorry, yeah. So yeah, so what
So
we
if
saw, right, is
I mean if it's like if it's Dirac delta function, then it is zero, right? Delta W.
yes,
It's
yeah,
Dirac delta, then it's actually zero, right? Yeah.
yeah, yeah. We will talk about this. So
No.
here,
It's not
this
zero. It's
delta
not zero. It's L. Sorry. It's not zero. It should be L. Sorry. Yeah. I'm sorry. Yeah.
L is something like it's a operator actually. I'm just writing
No.
in a
No.
something
What I
so
meant
that
to
we can,
say is, if
yeah,
delta
yeah,
W,
huh,
is that what you call delta W, or just what do you call that?
yeah, delta w, yes, delta w.
Delta W is Dirac delta function. Say that.
No. This is just some special function. Okay, okay. To reduce confusion, let me just write w. So w is some special function.
Okay. Doesn't matter. You can write delta W only. Please put delta W. Yeah.
Okay, because okay,
Just
so
say
I would,
fast.
yeah, I would not want you to get confused. Here, delta w is just like one function. So just the thing is, this is something known as a variation function. Like it's variations to something, and we will talk about this now. We will try to understand the meaning of variation actually. So we'll just have a little bit. Let's discuss about the meaning of variational calculus, because principle of virtual work is ultimately based on what you call variational calculus, isn't it? So we need the
Yes.
concept of what do we mean by variations in the first place. Okay, and this is what I'm calling as a special function, because it has some particular qualities or properties which is necessary, which we need to define beforehand, and then do all these calculations. So what we do is we have this special function which multiply and integrate over the domain. Now this has become a weak condition or a weaker condition. And we can clearly see, right, in the first place, this equation here, this one had to be satisfied at every point. Now this looks more like an averaging in an average sense, isn't it? In the average sense means, let me write one divided by the volume of bt, say some volume of bt. Bt is the body here, and bt L of x delta w dv is equal to 0, right? Here we see, right, it's something like an averaging operation, isn't it?
Yeah.
Some sort of a weighted average, because and the weight is given by this delta w. So what we see is it's more like we are just averaging and making the average to 0, equating that average to 0, and that it's more like a weighted average to 0. So this is the thing here. And since in this case, what will happen is at some point L of x won't be equal to 0. In fact, it won't be 0 at many places. However, it's just by the choice of w that when it is, say, at some point it may be less than 0, some places for some points it will be greater than 0. It's just because of the choice of delta w that when we integrate it in an integrated sense, it becomes 0. I think this is the subtlety here. I hope you have understood. I mean, please let me know if you have understood this. This is actually the crux here.
Yeah.
Isn't it? So at some point, L of x will be less than 0, means at what we'll see is in the majority of points, this L of x is equal to 0 won't be satisfied, which means this strong condition will not be satisfied at quite many points. However, by a suitable choice of delta W, we are able to make in an average sense, we are able to have this particular L of x multiplied with it integrate over the domain to be 0. And this is what is known as a weak condition. And this is actually the basis of finite element method.
Okay.
So in finite volume, the thing is finite volume method, right? If you I will just tell you that finite volume method is a special case of finite element method actually.
Yeah, that's right. That's right.
In finite volume, what we do is we take the weighting function to be 1.
Okay.
Yeah, so this delta W is
Because
equal to 1.
there
It
was
is for
this
finite.
no, I think even finite difference is also like kind of subcase of finite element. Is it not
Yeah,
right?
in that case, what we do is actually, okay. There is one more thing here. In finite element, right? I hope I'm not mistaken. We'll still think over it. In finite difference, we directly operate on the strong condition itself,
Correct.
in the sense that we actually change the differential equation itself,
Yeah.
because we are going from an infinitesimal limit to a finite limit. It's just like we are approximating the derivatives, isn't it? So before we were taking h tends to 0, isn't it? It's a limit f of x plus h minus f of x divided by h as h tends to 0. That gives the first derivative of f. However, when we have a finite h, then it is finite difference, isn't it? So in that case, we are actually operating on the finite difference itself. I mean, on the differential equation itself. So what happens is, as h tends to h, as we take very small step, right? So finite difference tends to be the most accurate method. It's more accurate than finite element, and even finite volume. Like finite difference is the gold standard. The only thing is we cannot have
Finite
that.
difference, I think finite element is the
No,
gold
no, no.
standard.
Finite difference is that is the very good thing about here, right? I mean,
No,
that
so I'll tell
finite
you maybe.
difference is the most approximate. It is the
No,
best method actually. Finite
so
difference.
I'll tell you. So I
Yeah,
mean, whatever I heard, like
yeah.
till today is like, so you have this strong formulation, okay,
Right, right.
and you have
Yeah.
a weak formulation. That's what we're discussing here,
Yes.
okay.
Yeah,
And weak
yeah, yeah.
formulation is like, so say that for the strong formulation, say you have d square x by d or d square f by d x square plus
Right,
something
right.
equal to 0, okay. And you
Yeah,
have
yeah.
to, in that condition, if you're solving the strong form, you have to
Hmm.
make sure that your function f is twice differentiable,
Right, right, right. Yeah,
right?
yeah.
Else, and if it's
Hmm, hmm,
weak,
hmm.
so if it is only
Hmm.
differentiable once, then it doesn't work. But when you take a weak
Yes, yes.
formulation, so for weak formulation, you put integral, you will do all the stuff,
Uh,
like you say solving the same problem. So you will end up with
hmm.
a differential lesser differential than the original equations, like you let df by
Yes,
dx.
yes.
Okay, so there you
Yeah.
can find a function which is just first order, or just has derivatives till first order. No, if
Hmm, hmm, hmm.
only that's what strong formulation and weak formulation is.
Right, 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 right.
That's
In
what I know.
finite.
That's what
Yeah,
I
yeah,
know. So
exactly. Yeah, you are
yeah.
absolutely right. The thing is, when we do weak form, then the requirement of differentiability, and we will later see that even requirement of continuity also becomes less stringent.
Correct.
Uh, the only thing is what we are doing, right? We are actually tampering with the differential equation in that case. In
Okay.
finite element and even in finite volume. The thing is, it's just because even we actually choose the weighting function from a limited set of functions that we define ourselves. And by that, we are also what you call reducing the requirement. I mean, making that requirement of differentiability on the solution. It's little less rigorous, isn't it? So it's like the differential equation was in second order. So it required second order derivative. I mean, it required the solution to be second order difference. I mean, twice differentiable. Now it's just first differentiable. I mean, just we need to. It should be differentiable at least once, isn't it? However, what we see is in finite difference, we are actually working with the differential equation itself. We are not putting any conditions there. All the thing is we are actually say when we define f prime of x. So we define as limit h tends to 0 and f of x plus h minus f of x divided by h, isn't it?
Mm.
Now, in finite difference, what we do is we just take h to be small, like h should be small. We don't know how much small. The only thing is as the more small it is, the better way, the more closer we are to the analytical derivative. Is it not? Isn't it?
Yeah,
So
yeah.
it's like, yeah. So then what we are doing is we are doing delta f by delta x. And this is equal to limit. There is no limit here. It's just that h small. H small. It's just like f of x plus h minus f of x by h, where h is small. And we call h is equal to delta x.
No,
So
so
here everything is just dependent on h itself. The finer
so
we
what?
take, yeah,
No, I mean, what I'm trying to say is, so I
yeah,
took this finite element course, and there he
right.
took the differential equation or partial differential equation, the Poisson equation or something, and first he
Mm-hmm.
approximated it with FEM,
Mm,
and later said that with just one condition, you will come
mm.
to finite difference.
Yeah, yeah, yeah. Yes,
You
yes,
understand?
yes.
But you
Mm-hmm.
can't do the vice. You can't do the reverse. It's like finite
Yeah, we
element
cannot go
is
the reverse. Yes.
more.
Yeah.
So that way I thought, okay, finite element is like big one, and all the other methods are like just
No, no, actually, yeah.
insignificant. I
Yeah,
thought
that's
that.
the no. The thing is, Dinesh, that you can never have any method which is more accurate than finite difference. Like finite
Oh,
difference
okay.
is the gold standard.
Wow.
The only
Okay.
thing we can, the only reason finite difference cannot be used everywhere. We know the the reason, right? It's because of the arbitrariness of our body shape.
Okay.
We cannot have such a mesh because finite difference requires pattern in the mesh, isn't it? Some pattern. There should be some pattern,
Yeah.
some
Yeah.
particular uh,
It's correct.
form, that some structuredness, or there should be some that is the most fundamental thing in finite difference.
Okay.
Otherwise, it becomes much more untenable to carry out the operations. It's like we cannot even have a finite difference schemes for arbitrary mesh. So that is the biggest drawback. So its drawback is just because all our practical problems involves meshes which are complex and or geometries which are complex for all practical problems. Require sophisticated meshes, isn't it? And then actually that actually just eliminates finite difference as a viable tool. So that's the issue we are not we cannot use. And when you see that even in turbulence computations and all, right, we always prefer finite difference. Say when we do turbulence calculations over a flat plate, all these standard shapes, isn't it? We always use finite difference. And all those high order schemes and all, right, sixth order, seventh order, whatever we hear, these are all based on finite difference, and all those computations are also done using finite differences. The
Yeah.
Now why we go for finite volume is because finite volume tends to approximate any geometry. It can be used, that method can be used to solve what you call all those flow quantities for any arbitrary geometry. And the thing is, it's very much designed for fluid mechanics. Finite volume has that tendency because we work with something known as a control volume, right? Because of which it actually makes finite volume very much suited for fluid mechanics simulations. Although like for past 30 years, there is a group who has worked with open form. or who develops open form, there is another variant called form extend. So a group of professors, there's like Jove, Jasak, and all those original developers of open form. They actually all parted ways gradually, right?
I don't
So
know.
yeah, yeah. As per the history of OpenFOAM, so initially they were like around 30 years back, the developers worked as a team, but gradually, because of their interest in different areas, they
Yeah.
all parted ways and made different variants of OpenFOAM. So one group is Jasak's group, uh, and uh, and also his peers. Now currently is before he was a professor in Croatia, and he is also a Croatian person. He's a from Croatia itself. But I think just yeah, I just saw last in just 2 years back he has joined University of Cambridge as a lecturer in scientific computing.
Wow. Okay.
Yes, yeah. Actually, he is one of those pioneers who have actually uh, who are actually promoting using finite volume to solve solid mechanics problems as well.
Wow. That's crazy. Okay.
Yeah, so the Foam Extend is the only software which uses finite volume to solve for structural problems. And the good, I mean, the thing is there are a lot of drawbacks in finite element methods for actually solid mechanics, which which is able to be mitigated, which are able to be mitigated by using finite volume even in solid mechanics. One of the problems is large deformation. So in large deformation, finite element suffers from a lot of problems in convergence and all, which is very much what you call mitigated using finite volume. So there are some very good features in finite volume, despite it being widely used in fluid mechanics and and people. I mean, people who work in solid mechanics, they hardly know that even finite volume can be used to solve solid mechanics problems and all. So like in my MTech research, I used finite volume method to solve for solid dynamics as well. I using that
That's
software
good.
that yeah.
Okay.
So that is the reason. So it's like however, from a very fundamental sense, finite volume is designed for it's almost designed for fluid mechanics problems. And the good thing about finite volume is it satisfies the balance of mass, right? Exactly.
Okay. Yeah, it actually conserves. That's what I.
Yeah,
That's what I hear.
exactly.
The
Yes.
equations are
So
exactly
finite
conserved.
volume. Yes, yes. So finite volume exactly satisfies conservation of mass. That is neither satisfied by finite difference nor satisfied by the finite element method.
Yeah. Correct.
So
That's right. Right.
yeah, and finite difference doesn't satisfy any conservation law.
Yes.
It doesn't satisfy conservation of mass, doesn't satisfy conservation of momentum, neither of energy. It's accurate because of its philosophy. I mean, because it works on the derivatives itself. So if some method actually works with the with the differential equation itself, we have a lot of power, right, to modify it as much as we can and
Yeah.
yeah, bring it as close as possible to the calculus, so to speak, to that calculus
Yes.
limit
Sir.
in that sense. So that is the reason that finite difference is the most accurate. And
Okay.
okay, so yeah. So we were just here, right? In an average sense, we talked about in an average sense. So this is what the philosophy behind finite volume as well as finite element. We always satisfy the governing equations in an average sense over the entire domain.
Okay.
Now what we'll do is now let's start trying to understand just very elementary introduction. I'll just give a very elementary. This has introduction to variational calculus. Yeah, variational calculus. And the good thing about variational calculus is it's still an active area of research.
Okay.
Yeah, I still see papers in all these Hamilton Jacobi equations still being published. Now that there's just people just trying to use it in different domains such as optimal control and all.
Wow.
And still, yeah, only the thing is we cannot take too much interest in every other area, right? Apart from ours.
Yeah. Yeah.
Like it's very interesting, but it requires a lot of time, and also I just read the abstract of the papers only. Yeah. So in variational calculus, what we do is, let me start with what is variational calculus, right? Fundamentally, let's just try to break down this the words itself. So variational calculus is, let me start some, let me draw some figure, right? In variational calculus, what we do is, given a function, right? We are given some function, say f of x, with some end limits x1 to x2. Now what we do is, variation calculus always we have something known as a functional. So like functional is the building block in variational calculus. Functional and then what we call variation. So functional simply says that we have some, I mean in a very crude sense, right? We define functional as function of a function. So it's like, say I of f is equal to integral over x1 to x2 of, say, function g of x, f of x, and f prime of x. So this is the most what you call most standard form of a functional. So you see, right? Correct. Here I happens to be a function, and it's a function of function. Yeah, you see, right? It's a function of function f. So usually what we do is we don't write like this. We write something like this in square brackets.
Okay.
So this is like, now what we do is, let's assume that, okay, we'll say that, okay, this I of f is some conserved quantity. Or it's, yeah, or as if it's some quantity. Let me just remove this. I mean, just some quantity I, which say has some minimum or maximum, or what we call as it has some extrema. Like the goal is to determine the function, something like you know that say, I mean, for this function f of x, we can easily find the points of extremum where the derivative of x is of f is 0, right? This we can easily do. This gives us extremum, points of extremum, isn't it? Yeah. Like from just basic optimization, these are like points of extremum. The thing is,
do di by df here, right?
yeah, here the thing is we need a di by df. However, this is not straightforward. You see, right? This is not straightforward. Why? The reason is, say I have this function f here. When we take the derivative of f with respect to x, we get and equate it to 0, we'll get certain points, like this point will be one of them, because here df by dx is 0. This point will be one of them. Even this point is one of them. Even this is one of them. The thing is, we are only dealing with one point. Now let's just try to understand from a limit point of view. Now it is, so say we have named this point as some sort, let's just give it a name, say let me call it a, or maybe xa. So what we have is x tends to xa, and then f of x a plus some quantity h minus f of xa divide by h. So now I can just call it h tends to 0. You see, right? What we are doing is we are just dealing with one point, which is xa. So we are just searching for a neighborhood about xa, isn't it? When we take the derivative, we we just go on this side, on the right hand side or left hand side, depending on the sign of h. If it's positive, then we tend to approximate from this side. I mean, tend to approach xa from this side. If h tends to be negative, then f of xa plus h will be less than xa. So we'll be approaching from this side. But all that we care is we are just trying to have this derivative and which we equate to 0. So which means that everything is done at a single point, isn't it? It's a single point. I hope you are able to understand. Please just ask me questions because this is very subtle here. Once you understand this, right, you have understood variational
I'm getting
calculus.
that. I'm getting that. Yeah.
Yeah. This is the only thing that's required. You understand this, you actually understand variational calculus. There is nothing in variational calculus. Then it's just about techniques, tools. This is the only crux here. So the thing is, here we are able to do it very simple. OK, we had certain points and we got the extremum. And then we can go for second derivative and decide whether it's minimum or maximum. We don't need to worry about that. For now, we just worry about where the first derivative is 0. Now, why we want first derivative to be 0? The thing is because first derivative of 0 gives us that, OK, there is certain points at which slight changes in the neighborhood does not affect the function, isn't it? So if we just little bit move right or left of xa, it doesn't change the function value. And you know, where we require this at many places, isn't in optimization problems and all. This just gives us some those critical points. However, when we talk about functional, the thing is, this is just a scalar and it does not depend on x, isn't it? I does not depend on x.
Why not?
You see that? I does not depend on x.
I mean, it depends on f, and f depends on. Yeah. Okay.
Yeah, but you see, right? We have already eliminated x from this by integrating over x.
Okay. Okay. Okay.
You see,
Okay.
right?
All right.
Yeah, this is the crux here. You see, right? So you see, OK, but it does not depend on x.
So what you're
Now,
saying is it doesn't depend which x point we take, like which limits we take,
yeah,
right?
exactly. Yeah, because it's all in an integrated. So after integrating, x just goes out of this. X is nowhere to be found. So it just becomes a scalar, just a single value. Now you will say, OK, how do I find derivative? What do you mean by the change in function? Isn't it? Say if we, this looks so absurd, isn't it? When we try to have di by df, try to have in terms of limit, f tends to 0, or say h tends to 0, and I of f plus h minus I by h. You'll say, OK, but what sense does this make? Like this, what does this mean? What does h mean here? Like,
H is a
what does
function,
f?
no? H is a function.
Yeah, but the
H
thing
is a
is
function.
now, yeah, another thing is, what do you mean? How do you make changes to the function?
Yeah. And does it, like, say that if f is a polynomial, x
Yeah,
square, should h
yeah,
also be polynomial like h square, like x
yeah. The
square?
thing
We
is,
don't.
how do you decide, right? That how do you make changes to the function? That's the issue here, right? Like, how are you able to take? Because I here does not depend anymore explicitly on f. No explicit dependence on f. That's why I have put under square brackets, because everything was already sorted out, right? After integrating, f was a function of x. After integrating it, there is not presence of f also anymore in I. Like the output that you get does not contain f or anything.
I mean, it's actually a value, no? Like, okay.
Yeah, does not contain f. So how will you find the derivative
Of f, you mean?
of I with respect to f?
Okay. So
Isn't it? You got the idea, right? That's the philosophy here. Once you get that idea, then you really understand. I mean, you have already understood Aristotle calculus. Then we'll just be discussing some tools, techniques, all that. But This is the only thing that has to be understood.
Yeah, so we can take a variation of f, like maybe add a
Yeah.
little
So
delta x
now,
value, delta x value.
yeah. So now we introduce the concept of variation, because now I does not contain f explicitly.
Oh, actually, add a function h such that it is equal to f of x1
Yeah.
at x1
So
and f of x2 at x2, but it is slightly more or less, or like it's just variation of.
yeah,
That's
it's
what.
like,
Yeah.
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 So I'll draw a new figure here, and I think this thing will get clear now. So what we'll do is, this was supposed to be bar f. I hope I mean little it's any arbitrary f. So this is f. This was the n limits x1, x2. So now what we'll do is, we will introduce variation. I'll use a different color. And we assume, what we do is, we have assumed that f of x2 is equal to some value f of 2, and f of, or let me just call it y2, and f of x1 is equal to y1. So these are fixed values. So y1 and y2 are fixed. So which means that if we introduce any variations, now we'll use that word variations. So variation is, we can, yeah, we can have some changes in f, something like this, right? But the thing is, at the end points, we are not allowed to have any variations, because y1 and y2 are fixed. And this here is f plus some epsilon into h. Now epsilon is a scalar and h is some function. You see, right? I hope you are able to understand this. So what we are doing is, we are just making changes to the function. But because the thing is, when we make changes to the function, it affects the value of the function throughout the domain. That's why you see that I mean, the values are different throughout the domain in general. However, at the endpoints, we are not allowed to make any changes. At the endpoints, right here and here, you see that here and here we are not allowed to make changes, because
Yeah, yeah,
we.
I understood that. Yeah, yeah.
Yeah. So now what
But
you see is,
we're not sure why. It's not why, but I think what happens if we have variation at such points?
at those points as well, you mean, huh?
Yeah.
Actually, yeah, that those things all come later. Actually, the only thing is, this will require another, I mean, an entire set of lectures.
Okay. Sure.
So what I'll do is, we will discuss this. I have the entire notes, because
Yeah,
I
no
did a
worries.
course
No
on
worries.
variational calculus. So I'll actually tell you all about that also. Like, what if then we have the concept of moving boundaries, what do you call, I mean, something like arbitrary boundary values. So when the boundary values, itself tend to be a variable. And in practical situations, we always have problems like that only, that you will have even boundary values changing. But here we are dealing with a very standard problem, very standard variational calculus problem, very standard one. So we have just fixed y1 and y2. Now you will see that uh, h has some properties, because we cannot arbitrarily choose h.
Okay.
The first property is, I think it's very much evident from the figure, right? Can h take any value at x1 and x2? That is the hint, I
No,
believe
it
here.
has to be equal to f of x1 and f of x2, right?
So what value can h take at x1 and x2?
F of x1 and f of x2.
No,
No, no, no,
h
no. Zero, 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 zero.
exactly. That's the.
Sorry, sorry, sorry. Yeah,
So
yeah.
it has that condition, that h of x1 and x2 has to be equal to 0. Second is, ideally, it should be at least as differentiable or as, or I mean at least the same order of differentiability as f, at least, because h can be
Correct.
a special function,
Correct.
right?
Correct. Because yeah, because we like the equations, you know all that. Yeah.
Yes, yes, that's the reason. Yeah. Otherwise, in general, we take h to be infinitely differentiable, but it should be at least as difference have the same order of differentiability as f. Now let's come to try. Now let's try to understand. Okay, now how do I uh, can I actually be able to take the derivative of I with respect to f? So that is, now we can pose that problem, isn't it? So what we'll do is we'll have I will so h here, right? This h is known as variation to function f, because
Okay.
we are allowing the function f to be perturbed using this function, right? By adding a small scaled version of h. So h is epsilon is just a scaling factor. The thing is, because it helps us to we'll see that why do we need epsilon. It's just for some, what do you call, what I'll do is maybe let me just remove this and bring some another function. Otherwise, I'm sure that there are chances of getting confused, right? So let me introduce some other function. G I've already used. So say f, uh, say let's just use p, because so that fh does not conflict anymore anywhere.
Okay.
So what we have is I as a function of, I mean, argument as f plus epsilon p. When we use this, we will have x1 to x2, and then inside the as an integrand we have x, and we'll have f plus epsilon p, comma f prime plus, since epsilon is just a constant, so we'll have just p prime into dx. Now what we'll do is, so here is the thing. Yeah. Now what we do is, let's have something known as limit of epsilon tends to 0. And before that, what we should do is, now what we see here, right, is epsilon p is here, f is here. However, epsilon is a small parameter, isn't it? Small is a small parameter. So like epsilon is very small compared to 1. So what we can do is, can we not expand the integrand here about epsilon is equal to 0? We can, right?
Yeah.
Isn't it? Now we can in within
So
as
yeah, do
a,
you Taylor series kind of g
yeah,
of x
exactly.
is
We'll use Taylor series.
like
Yes. So what we'll
x
do is,
comma f prime and
right. Yeah. So
plus that
yeah.
plus this.
So it's like we are doing some multivariate expansion, isn't it?
Oh, it's like
Since we,
so you call this I think this is like two linear equation. I forgot the name exactly what they use, but
ha
it's
ha
like
ha.
linear in two terms. It's like linear
Yes,
in
yes.
two variables. What do you call
Yeah,
that? I
yes.
forgot the name.
Yeah, I mean, at the very best, we can say that we can clearly say that it's a multivariate function, right?
Yeah,
Because
multivariate. Yeah.
yeah, because f and f prime are considered to be two different arguments.
Yes.
Okay. Now what we see is, yeah, we can use all that expansion. So x does not contain epsilon, so we are just need to expand about f and f prime about epsilon is equal to 0, isn't it? So first we have done this. Now we'll use epsilon, and now we'll just call it. Let me just see. Hmm, okay. So when we do this, then we have epsilon of p and partial g of partial x, not x, parcel f plus and then epsilon p prime, isn't it? And then partial g by partial f prime, because here we consider f prime and f to be variables, at least for the integrand, just for the integrand, this can be done. And then some higher order terms in epsilon squared, which we'll leave it as of now. We don't require right now.
Okay.
So this it can be expanded, right? Linear in P here and linear
But
in P prime.
but is G linear? Then what did you are you assuming that? This question I have to ask.
No, it's not linear. So all that those things we have put here.
Yeah, we're just doing yeah, TSC. All right. Okay.
Yes. Now here what we do is, now what we can do is let's do I of f plus epsilon g, sorry, epsilon p minus I of f, it's just f here, is equal to, we can have all this x1, x2, g of x, f and f prime plus epsilon p, g, partial g of partial f plus epsilon p prime partial g by partial f prime plus order of epsilon squared dx minus x1 to x2 g of x f f prime into dx, isn't it? Now what we see is the integrand in both the cases involve the same domain and the same variable, isn't it? Like we are using, we have the same variable x, or the domain is just from x1 to x2. So what we can do is we can club the integrands into a single one, isn't it? That we can do, right?
Yeah.
So in that case, this and this goes away.
I cancel that. Yeah.
So what we have is epsilon p partial g by partial f plus prime partial g by partial f prime. And what I'll do is I'll just take out of order epsilon square outside.
Okay.
It will be slightly modified order, but we are just considering about order, so everything goes there. Now what we'll do is let's divide both sides by epsilon. We can do that, right? Just divide both sides by epsilon. So what does this give us? X1 to x2 and epsilon cancels out, so we have p plus p prime dx plus order of epsilon. Now what we'll do is let's move a step forward and call it limit epsilon tends to 0. And we'll actually try to understand this graphically as well. When we have epsilon tends to 0, now you see the similarity, isn't it? In the single when we are just dealing with what you call that function f, and when we are taking derivative about some x is equal to xa, just like here what we are doing, x is equal to xa, we were just taking h to be tending to be 0, right? In that case, f of x plus h almost becomes f of a, isn't it? Isn't it? So yeah, so that same idea we need to carry here. So in this case, what's happening on the left hand side? What we are doing is we are actually bringing, so this was the perturbed function. So this was perturbed function, say perturbed function is f tilde. As epsilon tends to 0, f tilde is tending to f, right?
Yeah.
So it's as if we are actually approaching the original function.
Okay.
And in that case, what happens is this becomes 0.
Correct.
This also tends to 0 as epsilon tends to 0.
Yeah.
So what we clearly see is this here is what we call as
variation in
the variational derivative, and it's known as the operational form of variational derivative. So, but for now, we'll just call it variational derivative. Because whenever we need to find derivative, actually we have to use this method. Although there are one method is get your derivative and all, but those cannot be used. I think this is known as get you. There is one called as fresh air differential, but those are not usable. Like these are all just for mathematical purposes, cannot be used to determine the derivative of any, I mean, determine variationality. So this is what we actually use in when we tend to find variational derivative. Now you clearly see that, okay, but that's fine. But there is something else also on the right hand side. Could you please tell me what do you see something on the right hand side? There is some quantity.
Mm.
There is some quantity, some unknown quantity. Like ideally, differentiation operations should not introduce any new quantity, right?
Yeah, so
So here there is some quantity when you look closer. Which is that quantity?
so huh, what is that quantity?
Yeah, which quantity is here? Which new quantity? When we take a look at our there is this is the expression of that functional. However, in the derivative, there is some quantity appearing right on the right hand side. Some
Yeah.
quantity. Which is that?
So it's like it's actually the variation. It's like change in I with respect to the reduced perturbed function, right? That's what we have interpreted it to be, right?
Yeah, I'll show you.
You're or not audible. Okay.
No, I'm not audible. Huh?
Okay. Sorry, no, you. I thought you're talking, but I can't hear you.
Okay. Now here you'll take a look at this functional. Okay, just
Ah,
take a look. And now you go back here. Do you see something new here coming to the picture? Which particular, there is one new quantity coming in this picture, right? In the integrand. Which is that?
this full quantity is new, no?
No, new in the sense that look at the form of G here. And the integrand is this.
Oh,
Yeah, I think I have got now. You have got now. What is that now? Now tell me.
you additionally have variation of G with respect to F. That's what I see.
You see, right? Some new quantity, which is
Uh, it's like it's not it's variation of G with respect to F.
no, that's not the new quantity because the thing is we know we know the functional I mean dependence on of G on F and all. However, you see there
Oh,
is one new quantity here, which is
you should tell me when I tried. Yeah, please go ahead. I will try
just
it.
tell
I
you,
might
man.
know
I
it,
mean,
but I might know it, but I'm
uh,
not finding it. Yeah.
okay, look at the expression here and look at the expression here. Just the terms and all terms and whatever is occurring, all those. You see some quantity here, right?
Mm.
Which quantity is newly introduced here, which was not before?
P and P prime.
Exactly.
I mean, they're obviously new.
Yeah.
No.
So P is unknown actually.
Okay.
So there is the issue here that how can
No.
a variational
Also in a way, like
uh,
I mean, there's a nice way to look at it. If you look at dimensional kind of thing. So it's like
hmm,
G. You're taking so what you're trying to do is. So when you take this integral, we're trying to find the variation of G. It's like dg times dx. So
yeah,
ultimately,
yeah,
you'll get change in G, right? It's
yeah.
like change in G in that integral area, but change in G with respect to the function inside it, like G is a total integral,
Huh, 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 huh,
and you're multiplying it with F. So you're ultimately getting like what function should I multiply with
huh.
so that I get like if you make it this equal to zero, like if you're trying to find a function F, right?
Mhm,
So that
mhm,
if you make this full thing to zero, you are following me. I mean, you already know this, but am I
mhm,
making
mhm, mhm.
sense? Am I making sense?
Yeah, 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 yes.
Right? Am I making sense?
Huh,
So if you
yeah.
make this left hand thing to zero, say that you make this left hand thing to zero.
Exactly. Yeah. Yeah.
So what we're trying to find is we're trying to find a function p
Yeah.
such
Huh.
that when you multiply it with this quantity, like p times dg by df plus this everything,
Hmm.
like so that that function f will make this to like the maximum that you could find the maximum variation in I,
Hmm. Hmm.
right?
Hmm. Hmm.
That's what
Hmm.
we are trying to find. I think that's what you were going as well. Yeah.
Yeah. Yeah. Yeah. Yeah. So our goal again is to just find like such a function, right? Like our goal is to find even f is unknown.
Yeah, f is also unknown. Yeah, exactly. Yeah, that's
Yeah.
what. So what
So
is so
yeah.
how would you find both p and f? Huh? Okay,
Yes. The only thing is we have one equation, so we'll see that no, we cannot determine one of
both.
them.
Yeah, correct,
So
correct.
we will actually just let's go through the I mean the what we call uh, this derivation. Now we'll actually see that. So what we see here is that p is also unknown. So it's like we have just one equation. And since our goal is we need to determine the extremum or f, right? We need variational derivative to be zero. And this we can compactly we can just write it something like this: d of f plus epsilon p as epsilon is equal to zero. This we equate to zero. So this should give us a condition for determining f. However, what we see is we have also introduced a new factor p or a new quantity p. And that's again another headache. So what we see is, so in this case, what we see is, I'll rewrite again here, that di by d epsilon, f plus epsilon p, epsilon is equal to 0, is equal to integral of x1 to x2 and p partial g by partial f plus p prime partial g by partial f prime into dx because order of epsilon that term became 0, so we have this much. And because of the presence of p right here, the thing is I was not prepared to go through this line the way we are approaching things, right?
Okay, no
So now
worries. Yeah.
I'm just introducing new terms, right? Now I introduce something known as a directional derivative.
Okay.
Just a slight digression. I just like I'll just take 2 or 3 lines. What do you mean by directional derivative, right? That's the first question that comes in our mind. Now, what's directional derivative?
Like
So the thing is,
the
yeah, yeah,
maximum
yeah.
change, like the direction in which your function is changing maximum.
No, that is known as gradient.
Oh, directional derivative is then it's like I
You are
think it's
actually
like
very,
change,
very
like
close
it's just
here.
a change,
Yeah,
right? Yeah.
yeah, you are very close actually. So directional derivative, right? So suppose,
It's gradient of f, no? Direction derivative is direction gradient of
yeah,
f,
say,
no?
yeah, yeah, yeah. But we'll see.
Okay.
I'll just tell you. I'll just tell you. Yes.
Go ahead.
What we'll say is we are very close actually. So say we have some function q of something is equal to 0. Just q is equal to 0. I don't want to put arguments and all. Just q is equal to 0. And then so this particular the thing is this is locally normal, right? So this
Yeah.
gives us grad of q, isn't it?
Okay.
Now grad of q is always locally, I mean gradient always gives the local normal direction.
Yeah, maximum change. It's just yeah, maximum
And
change.
that's what causes maximum change. Yes.
Hmm?
Yes. Yeah. So this is like 90 degrees. What if we wanted to find the derivative along some other direction, say a vector,
Yeah, that's what it says. Yeah. Correct, correct. That's right.
isn't it? So in
Mm-hmm.
that case, what we will do is, so the directional derivative of q so will be along a direction. So for directional derivative, we always need some direction. Along a vector will be grad of q dot a. So this is the change along a direction. So this is the change of Q along A direction.
Correct.
Right?
Okay, so it's like if you take gradient of Q
Huh.
dot
Yeah.
gradient of Q normal vector, like normal vector in the direction, so we'll get the change in the
Yes.
normal direction, right?
Yeah. Actually, to just to clear your point, right? What you are saying is, so say we have now. You'll ask me, okay. I mean, there is one question here that why does gradient give the maximum change?
It does.
Isn't it? The thing is, it also is a product of derivation only that we are actually able to show that. Now, what we say is, what if A is aligned along Q?
Yeah, that's what I'm saying. Yeah.
In that case, it becomes
Yeah,
and
it gives maximum change, no? Because the angle is,
yes,
yeah, the angle
yes,
is the zero
yeah,
and cos is one, and you
right,
get
right. It's all
maximum.
about that. Yes,
Yeah,
yes.
yes, that's right,
So
that's
this
right.
is always less than Q into A, right? Now, what if A is aligned along Q and A happens to be now? I'll just do this one, right? Now let's just let A be some unit vector. Then it actually simplifies things. Be some unit vector, right? Along A, it's some unit vector. Then this is will be 1. But if we put equality sign, then we'll have cos of grad Q comma A, isn't it?
Yeah.
Depends on the angle. And then we'll see that if A is aligned along grad of Q, then this particular becomes 1. When A is parallel to grad Q, this implies that cos of grad Q comma A is equal to 1, isn't it? Because 0 degree. There is like the angle between grad Q and A is 1. I mean, is 0. Because of which cos is 0. And that's the reason which means that this actually becomes attains its highest value, it is grad of Q. So this is the I mean, what you call subtlety here. It's actually first we define directional derivative and then we are able to define why gradient gives the maximum change in that quantity. I hope you are able to follow. Should I repeat and in any step?
Yeah, of course. Yeah.
You followed, right? Every
Yeah.
step. Yeah, so that's the reason. So now we actually understood the meaning of directional derivative here, but this is for a vector or what we call as finite dimensional calculus.
Okay.
However, what we have been doing is infinite dimensional because f is a functional, right? Any function is infinite dimensional because you cannot actually prepare a list of values, isn't it? You cannot have a list of values. For infinite dimension calculus, we can always have a list of values, isn't it? Say if you're in Euclidean 3D geometry, then that list contains 3 numbers or 3 components, isn't it?
Good.
However, in infinite dimensional, you cannot create, say, for a function which is defined f, right, over R to R. And in this case, x happens to be an element of x1 comma x2. In this case, x from x1 to x2 has infinite numbers, isn't it? Within the list, because of which we cannot have f as a single list, and it will contain infinite number of entries. So that's how I tend to define infinite dimensional and finite dimensional. That's how I say it. Yeah. So. So based on that, what we are doing is we are just trying to link trying to understand directional derivative here. So we have been able to show that, okay, how should we write this? We can write as uh, like grad of Q. Say just in this case, it just happens to be inner product, isn't it? And this gives us of directional derivative of grad Q along A. This is how we read this or interpret it, isn't it? This particular thing here. Now, similarly, right? Similarly, let's try to even have this, what we have written here, try to interpret in the same manner. So what we tend to do usually is this one we write as I as a argument f, comma, You are able to follow, right? Just
Yeah.
try to relate this and this. Or sometimes we also prefer to write delta here, which means the thing is we are looking at variation of I
Variation. Right, okay.
along P. So when we actually equate this to 0, isn't it? We are actually doing this. This gives us the condition for extremum. What extremum? Extremum. Extremum uh, for what? For F, because the thing is we need F, isn't
It's
it?
like you get what is the value of f so that like I is maximum. No,
Right.
correct? They just like
Yeah,
the previous one only. Yeah.
yeah. So we want we want condition for F. We want to
Yeah.
get F. And I mean, as we progress, I mean, in a few steps, we'll able to get that condition.
So it's just like in gradient of q. So
Uh,
we're trying to like gradient of q is gradient of q of x, right? We're trying to
right,
find
right.
the value of x, which
Yes,
actually
yes.
gives us maximum value of q such that it is zero in
Yeah.
like you know.
But yeah, you know what, Dinesh? Now let's not introduce maximum here. Let's just call it extremum.
Okay.
Extremum
Maximum.
can be max, minimum, or
Yeah,
saddle
yeah,
point.
totally. That's what I mean as well.
Yeah.
But here there's a conflict. Do you see that? Not a
Yes.
I don't know if it's a conflict, but let me put it like this. So here it implies
Uh,
for given x,
yes.
we are stating that there could be many a, but no,
Okay.
right?
Okay. Let me clarify a
Do you
bit actually.
understand? Do you understand what I said
Yeah,
that right?
you are right. You are right. So I'll just
It's
write.
not,
Let me slightly add something actually. Now, when we talk about this condition, even in this case, when we find grad of q comma a, and when we find the say the extremum point of q, right? Or sorry, the points, whatever. Say if had it been just had this q just been a function of x, had this been just a function of x, just please bear with me that in this case it doesn't make sense. So I'll just that's why I have not used any argument. So if we wanted to find the extremum points at which q at which what you call the change in q is 0, so to speak. Uh, just please bear with me. I may not be mathematically literate here. Just we are trying to locate those points at which change is 0, because that's what gives us the point of extremum, right? As we just saw here, right? We are by taking derivative and equating to 0 gives us the points of extremum. Likewise, here what we do is we are looking at grad of q along some direction a. However, you know that if we want something to be extremum, we want that the directional derivative along any direction should be 0. Any direction.
okay. Oh, it's any direction now.
It should be any direction. So that's why I write this should be, I'll call it for all a. It's only if the thing is if we have the directional derivative is equal to 0 in any direction, what should be the logical conclusion from that statement?
Directional derivative to be zero for any
Any
direction.
direction. So does that ring a bell? Does that tell something about the condition? There is some
See,
condition which comes. Uh-huh.
see, I'm trying to think that it's
Yeah, yeah, yeah.
like both
Yes.
are zero, but for any like it has to be zero for any a.
Yeah, for
So what
any,
condition does it put
what should
on
be?
Q? Yeah, that's what I'm thinking.
Yeah, exactly. Yeah. So what does that tell us?
So for every direction, if like it's like say that you at a point you found that Q is maximum
Uh-huh.
and maximum or extremum,
Yes,
and
extremum.
you are
Yes, yes.
saying that whatever direction you go,
Huh.
like A is the direction here. So whatever the
Yeah.
direction you take, so the variation is zero.
Yeah, yes. So it tells us something, right? What multiplies with some non-zero quantity to always get zero? I think that was the
Zero.
hint.
A should be zero.
Exactly. Yeah, exactly. So that is the thing here. So which means that the only uh, deduction here is conclusion is that grad of q itself has to be zero. So likewise, we are looking in the same fashion that we to determine to get the condition for extremum for f, we need this particular thing to be zero for all p satisfying certain properties which we saw, right?
But
That at the
this is it's a bit confusing actually. So
no, you'll actually see that they are very
no, no, I
one leads
understand.
to the other.
I understood. No, this no, I was very clear actually. It's not that confusing. But one more question I have here is in
Yeah,
the figure which you drew here, like you drew a curve and you have gradient of q
yeah,
at
this
a.
one.
No, no, niche, just bottom.
Okay, this
No,
one. Okay.
there. You find it like this small figure you drew there, right?
Yeah, this
Which has
one. Yes,
a unit vector
this
and
one.
x
Yeah,
and
this
a.
one. Yes.
So
Uh,
there, what you're saying is gradient of q is equal to zero.
right. Yeah.
Okay.
So instead, right, I'll not call this one. I'll just call this some surface q. I think that should resolve either because we were looking at okay, how can function be zero and grad? So let's
Yeah,
just
that's
reduce
what I
this.
was thinking as well. Yeah.
Yeah, I think now this should be clear. I mean, now it should be more this one.
This is not easy. Okay, let's go ahead. Yeah,
Yeah,
that's okay.
yeah.
I'm fine.
So this is the connection here.
No,
So
why
if you
I'm
want to
saying
find,
this is no. Usually in our cases, it's not
hmm,
that at a point gradient of q is not zero. Gradient of q you'll have some value, but only in that in particular direction, which is like gradient of q direction, you will have that gradient of q is extremum, right?
yeah,
You
no, the
you
thing is
understand?
it gives us the extremum for q. So what do we mean by extreme?
No.
Extremum
See,
is
see, see the point. Say that you take a function q. Okay, it's like
uh,
three-dimensional function surface.
hmm, hmm.
Okay, and say that you're trying to find the direction where q is extremum. Then you take the
Right.
point, and you'll get gradient of q. Uh, and at
Hmm.
that point, gradient of q is the direction.
Hmm.
Not it's not directional derivative. The according to us, I don't know what you call it. It's actually gradient. It's like yeah. So it's like gradient of delta q, which gives us
Uh,
the maximum variation of change in q. It's not zero,
yes. Yeah.
right?
Yeah.
So gradient of q is not zero actually. But here we are again bringing this what I was
Yeah.
trying to.
Yeah. The thing is, when we look at extremum, right, we always look like those points about which if we perturb a bit, right, it will not change the function value. You understand the point, right? Let's go back to our figure here. You see, right? Like in this point that we are considering here, uh,
Okay.
if we move even slightly to the right or left of xa, it does not change the function value, right?
No.
So that is the thing that we are trying to convey here. That extremum are the points of extremum are those points about with slight excursions about that point. If you move little bit left or right to the about that point, it will not change the function value. Slight means very small, just like epsilon distance on the right or left.
Okay.
And that's what is mean that what is concluded from this, that the derivative at those points are zero. So derivatives at that point are at those points becoming zero means that about slight, I mean, in the immediate neighborhood of those points, the function value won't change. That's why it's right, because the way we understand this thing is this quantity here is rate of or the change of f with respect to x. So the change of f with respect to x about certain points, if it happens to be zero, then those points are called as points of extremum.
Yeah.
So like if I just zoom this, right, you'll find that it will appear as if it's locally flat.
Yeah. That's right. That's right.
So
And I
X.
think I think I got it. Yeah.
Yeah, so that is the thing here. So that these ideas we want to carry out to even when even to functionals. So the thing is, so what we clearly see is here we told that okay, if grad of or if the directional derivative of q along a sorry, actually I had made a mistake here. This is known as directional derivative of q, actually q along a, because we are looking at the rate of change of
Yeah.
q.
Yeah.
Yeah.
In a direction. Yeah. That's why it's
Yeah,
directional.
yeah, yeah. This is yeah. No, I think I think this must have reduced the confusion. It should not be grad q. It should be
No, it
q
is clear.
actually.
You're right. You're actually pretty right. Yeah. It's not
Yeah.
long.
So directional derivative of q along a, if it happens to be zero for all a, then it simply implies that the gradient of q is itself zero, which means that there is no change in q in that about those points. I mean, about those points which we will compute from this condition now. So this will give us the points of extremum. This only remember that this happens only for finite dimensional what you call calculus. In infinite dimensional condition calculations, we do not get the function. We just get the condition for that function. And I will come to that actually now. So just extending this idea to here. Here now what we see is if the variation of I at some function p for any p, sorry, at some function f for any p, if it happens to be zero, then it gives us the condition for extremum, which means the condition for extremum, which is f.
Okay.
And this should be for all p satisfying certain conditions. Here p cannot be arbitrary. Why? Because p had to satisfy that these two conditions, right? Which first one is the most important one in the sense that at the endpoints it should take the value of zero. Okay, now let's come to another slide here. Now I'll just use the expression. I'll just copy this expression here, this one. So I'll just write it as x1 to x2 p plus p prime dx is equal to 0. Now we can do something more. Let's separate this two into two separate, two different integrals, and just take a look on the second integral. P prime partial g by partial f prime dx is equal to 0. Now, what I want, our goal right now is we want to eliminate eliminate in the sense that we want to have terms only in P. We don't want P prime.
Okay.
So you know what we need to do, right? There is something known as integration by parts, isn't it?
Yeah. Okay.
So integration by parts will remove P prime from here and will make it P only. So x1, x2, P partial g by partial f dx. Plus in this case, what we'll do is we will take first function to be P. Sorry, first function to be this one and second function to be P prime. So let's do the first step here. So in this case, it will be partial g by partial f prime into P, right? Because we integrate P prime with respect to x. These values at x1 and x2 minus, then we have to differentiate the first function, right? I'll just add the formula here. uv dx is equal to, or rather uv prime I'll write is equal to uv x1 x2 minus u prime v dx, right? This is the formula, right, for integration by parts. So here u is partial g by partial f prime and v is p. Okay, and then in this case, then will be d by of dx of partial g by partial f prime p dx x1 to x2 is equal to 0. And in this case, let me always write that thing actually, so as to get the idea. Now what we can do is, this implies that now we see, right, even in this case we have p and here as well p. So we can actually merge both of them, right? Both these into a single integral. So we can call it partial g by partial f minus d by dx of partial g by partial f prime into p into dx plus partial g by partial f prime p x1 x2 is equal to 0. So now what we'll do is, let's look at this particular term here. What is the value of p at x1?
0.
And what is the value of p at x2?
0.
So does this quantity even matter?
No.
So which means that this term is 0.
Okay.
So what I'll do is I'll just cross this out using some other color. So what we are left with, that this term has to be equal to 0. Now let's come back to the question that we are discussing some time back. Here I said that if the inner product of grad q and a happens to be 0 for all a, what does this say? It says that
Grad Q is 0.
grad q itself is 0, right?
Yeah.
So look at this expression here. What do you suggest now? If I want this expression to be 0 for every p. Hello?
Sorry, I
Yeah,
just.
sorry. So if you want this expression to be 0 for every p,
Okay.
there should be some condition, right? What does this gives us something.
Yeah, so internal that has to be 0, no? dg by dx minus dg by.
Exactly. And actually, we just use our reasoning here. However, it follows from what is known as the fundamental theorem of calculus of variations. Sorry, fundamental lemma actually, yeah. So this has to be 0. And this is actually known as fundamental lemma of calculus of variations. This is the most important lemma in the entire field of calculus of variations. The most important result. And this actually we can actually prove it, but because we don't require it now, we'll just use the result. So you see something, right? That this did not give us f. It did not give the expression for f, right? However, it gave us some condition on f. The thing is, this gives us a differential equation in f effectively, which we solve it to get the expression for f. So this is known as, this is often written as actually this is the actual variational derivative of f, because the variational derivative should be independent of any direction, right?
Yeah.
So this term is also known as the variational derivative. So this term can also be denoted as variational derivative of I with respect to f. Mind you that this does not mean anything like you understand my point, right? This doesn't, you cannot actually visualize this. However, you see that this term is independent of any new parameters, isn't it? That's why we call this as variational derivative of I with respect to f. This is the actual variational derivative. However, this is not used per se. I mean, we only use it to get all the extremum points. But in that sense, however, we call this as this to be the variational derivative, this entire expression to be the variational derivative, or what we are referring here, right? That this term is the variational derivative. Wherever you find this is known as the variational derivative. However, variational derivative always involves direction. So we always have to specify variational derivative of I at f along this particular direction p. Okay, I think with this introduction, now we can come to principle of virtual work. Actually, this was just a very basic introduction to calculus of variations, and we also linked it to finite dimensional calculus. Now we are in a right position to work with principle of virtual work because it uses these concepts. Principle of virtual work. So in principle of virtual work, what we do is let us pick. Let's go back to our balance of linear momentum. Because everything is hidden in balance of linear momentum, right? It gives us everything. So in that case, what we had is u a row x double dot vector is equal to divergence of sigma, which is the Cauchy stress tensor, plus b vector, which is b vector is the body force vector. And what has been done, right, in this particular set of lectures, that we only deal with static problems.
Okay.
So static. It can be done for dynamic, but the thing is, I think the instructor did not find it like having even dynamic term makes the system much. I mean, it looks expression a bit complex, but that does not change the philosophy. Actually, the philosophy still remains the same. So in static formulation, what we do is we'll have this term to be 0. So this means that all we are dealing with is divergence of stress tensor plus b vector is equal to 0 vector.
So I think so these kind of problems more deal with when the body deformed and then we're looking at the stress.
Yeah, in a very what we call as quasi-static loading, right? That it's deforming very slowly, such that the time derivative is almost close to 0, isn't it? Now, let's go back, right? Where we had introduced something known as multiplying by something, right? I think now you understand why what this is known as the variations in function.
Yeah, so it's like okay, it's like that little change
Yes.
which you
Yeah.
take, but still L is like
Yeah. Which.
find the value of x,
Yes.
or
Yes.
yeah, find the value of x such that L is maximum or L is extremum,
No, no,
such
no.
that
Here the thing, yeah, yeah. Here the thing is it's slightly different in the sense that I wanted to introduce the concept of variation from here. However, what remains is that L of x. I think you are right. So L of x is similar to the variational derivative. Yeah, you are right. You are right. Yes, Dinesh, yeah, you are right.
okay. So it's like
Yeah.
so
So
we're trying to find the not trying to find. It's like what value of x will give me the maximum variation in L.
yeah, actually,
Right.
that is what is the differential equation. That's what is differential equation. So that is what this one. So when we talk, I mean, we discussed, right, about
Yeah, that's what
this
differential equation is.
quantity
No,
here,
yeah.
this quantity. So the thing is, what we call as the governing equation, right? So governing equation is nothing but variational derivative I mean equated to 0. So this here, right? This here, this one, this quantity here,
Okay.
this one, this is governing equation actually.
Okay.
You see, right? We'll actually connect these ideas. So governing equation is nothing but variational derivative equated to 0.
Then it will be dl by dx minus dy
Huh.
into dl by dx prime, right? Equal to 0. That's how
Now
it
the thing
should be.
is, no, the thing is L was an operator actually. I think I had mentioned here that L is a linear operator. I had mentioned here, right? Linear, it's a linear operator.
Okay.
So Linear operator means it can take any form, any operational form. Like
So it's like
I
g
mean,
of x comma f prime, f of x comma f prime, right?
exactly,
It's like
exactly.
g, right?
Yes,
It is like
yes.
g.
Yeah, it's
Yeah.
just an operator. Yes. So I'm sure that you must have seen, say, when we write this one, right? Convection equation. Say L of partial u by partial t minus alpha partial u by partial x is equal to 0. This can also be written as L u is equal to 0. And then we have to L the what do you mean by L? L actually stands for linear operator, and you'll see this widely used. Usually we write in script, so like this, so linear operator. And the thing is, if we have nonlinear operator, then we tend to use some other symbols. Now, where L being an operator, it will have some form as say partial by partial t, some argument minus alpha partial some argument by partial x. So when L acts on something, I mean, then it just I mean, it just fill in all these parentheses. So when we have LU, then it will all these parentheses will contain U then. So this was just a linear operator. So when we are talking about L of x here is equal to 0. So L of x is equal to 0 was our variational derivative equal to 0, or what we call as the L of x is equal to 0 was something was that governing equation. So in this case, in that sense, this one was L of this one was L of x is equal to 0. And when we see look at clearly, right, we actually able to see that actually sigma also ultimately depends on the Poisson vectors, right, of the material points as it deforms. Isn't it? Because sigma is related to strain. Sigma happens to be a function of strain, and then
Yeah.
strain is a function of displacement, isn't it?
Correct.
So
Correct.
these are ultimately related, yeah. Isn't it? So what we'll do is we'll go the reverse way now. Before, what we are doing is we actually obtain the strong condition, or what we now we'll go backwards. So in backwards, what we do is we have this strong condition. This is actually the strong condition.
Okay.
So what we'll do is we will, since there is a vector quantity on the right hand side 0, what we do is we multiply both sides by some variation in the displacement. And this side as well. Let's go back. That's what we did right before also. So this, I mean, delta v vector is something like p.
Okay.
You see that in this case we were dealing with just scalar things. Now we are dealing with vectors. So in that case, even the variational function will also be uh, vector. Actually, it's like a vector field. It has three components which are all scalar field, scalar functions like delta v con contains delta v1, delta v2, and delta v3, all of which are scalar functions. Okay, just for simplicity. I mean, we are just for notational compactness, we are doing this. Now what we'll do is we first multiplied with both sides with respect to some variational what you call function, and this has some properties which we'll come to deal with later. Right now, let's not touch that. It just spoils the flow, right? It has some properties because even in the previous case we saw that P had some properties. So even in this case, delta V vector has some properties. And then what we do is we integrate over the domain B.
Volume. Okay.
Exactly, over the volume. So we'll have this dV. Or for just D capital V, let's use. And on the right hand side, no matter whatever we do, it will always remain 0, right? Because it's any operation on 0 will always keep it 0. Now, and this is what we call as virtual work. You see, right? Before it was force into, something like force per unit volume. Sorry, something like, yeah, like divergence of stress we'll actually make it Newton per meter cubed, right? Because stress was Newton per meter squared. Taking divergence actually makes it Newton per meter cubed, isn't it?
Yeah.
So what we do
Correct.
here is, so it's more like a force only.
So it's like, okay.
When we multiply force with some displacement, it gives us
Energy.
work, right?
Yeah.
However, this is virtual displacement. So virtual displacement is like we are under. I mean, we had studied this in an undergrad, right? About virtual displacement. So virtual displacement is nothing but variation. Actually, virtual displacement is a variational function.
Yeah.
So when we link the ideas, right? So virtual displacement. So virtual displacements are those displacement which we do not actually provide to the system.
Yeah. Yeah.
It's just that by its name, it's just virtual. We are just imagining that displacement to occur. And because of
So
which we, yeah, because of which, so say you have a system in which you provide virtual displacement. Obviously, virtual displacement will not do work.
correct.
So that is why we call the corresponding
So
work
it's
as
like,
virtual work.
we're trying to find a solution for this equation. Maybe you're trying
Right.
to find sigma. Are you trying to find sigma here?
Yes, yes. So sigma in terms of displacement.
Sigma.
Yeah.
Correct. So
Yes.
that such that is like maximum variation. So
No, we are not
right.
doing. We are just doing in an averaging sense. No, what you? I mean, there is some big issue in very. I mean,
No,
whenever
no.
you.
What I'm trying to okay.
Yeah, I got your point. Now let me just rephrase it. Right. So
Okay.
there is some issue in whenever we use all these variational calculus in solid mechanics. The thing is, we never worry whether that particular solution is maximum or minimum. By default, we always assume it to be minimum. And
Okay.
that's why you must have heard the concept of principle of
Minimized
minimum
energy.
potential energy and all that.
Yeah.
The thing is, no one checks the second derivative. The only thing is the second derivative gives us idea about stability of a system. And that's something we are struggling with in my PhD project right now. Like we don't know how to
Okay.
determine the second derivative of the functional. We got some ideas. Uh, However, the thing is we are unable to generalize it. And there is no there is no what you call work in the literature because because finding second variational derivative is a very complex task.
Okay.
So no one, I mean, no one in the mechanics community usually touches that. You won't find like there will
Okay.
be, so people in pure maths will do that, but the thing is, you know, the ideas of pure maths we can hardly apply
Yeah.
it anywhere. Because they
Okay.
only deal with bonds and all, but we don't need bonds. We need numbers.
Okay.
Yeah. So
It's more like proof. They will just take some small part and they'll just say, "This is this."
exactly.
I mean, I'm not. I mean, I don't know much. I shouldn't comment like this. Like
No, no,
whatever
but
they are doing,
you're
they
right. Actually, you're right. Yeah.
just take
They.
small part and they'll say, "यहाँ पे ये proof this change that," and
Best,
this
best.
is how it is. But you're doing, you're taking this, you're trying to go till applications.
Yeah,
It's like
and because we need
lot of work.
numbers, right? For us, we need numbers.
Yeah.
As being an engineer, we need numbers. So there is where, and you saw right that p is arbitrary, right? Here also you saw that p is arbitrary. But in the thing is in second derivative, when we find the second variational derivative, then p can no longer be ignored anymore.
Okay.
Here we use the fundamental calculus of variations to eliminate p, get the condition on f. But in that case, the thing is the nature of p also starts affecting the problem. I mean that particular situation. That
Okay.
the p actually gets so what you call entangled with other terms, right? That we can no longer separate it in the second variation.
Okay.
So then we get stuck. Then here we were actually able to by integration parts separate p out. In the second variational derivative, we are no longer able to separate it like this anymore. So then the complexity starts coming into picture, and then it becomes very, so finding second variational derivative is very problem specific. So for every problem you'll have, you cannot use the same method in every problem, and because of that we cannot have a general form also. We cannot have a general technique or a general approach.
Okay.
So it becomes very particular in nature. It's like problem specific second variation method. Yeah. So coming back here, right? So here when we multiply the virtual displacement, we are actually doing again in something known as averaging sense, and you are actually clearly able to see here that when it's just like equating some weighted average to zero. You able to see, right? We are clearly able to see here, right? So if I divide this term here by the volume of the deformed body, then it's like weighted average.
Correct. So it's like, yeah, it's like we're trying to find the work done by entire forces
Yeah,
on
and
such
equating
volume.
it to zero. Yeah, the thing is because virtual displacement won't create it won't create real work, right? It will also create virtual work. The only thing is if the body is in equilibrium, then you
Okay, so
cannot
that
have
implies, it's like we are at minimum potential and find the
already,
stress
yes,
value sigma such that
yes,
the total work done is zero, right?
exactly,
That's what we're
yes, yeah,
trying
that's
to
the
say.
correct,
Mm-hmm.
yeah, that's the correct interpretation. So which means that's how we relate this back to what we are discussed now, that the variations in the functional, because work done is also a functional. So variation in the functional should be equal to zero. And this we can write actually as W as a function of X vector. They have never, in this entire notes, I have not seen uh, how they have defined, I mean, the expression for displacement. So that's why I'm just using X itself. So like this is something like this expression can be written as this. These are equivalent statements, equivalent expressions. We see clearly, right, that the variation of W at X vector gives the state of deformation for minimum potential energy along any direction delta V vector is zero. So this is the principle of virtual work.
Okay.
And they have done all the expansion and all in the notes. So I will just go through, but we'll just try to, we'll not try to derive everything. We will just try to connect with some of the ideas.
We will stop here. What do you say? Because
Okay.
no, it's not. No, we just stop here because this is actually good. Whatever discussed here, we covered a lot actually.
Yeah, and I mean that
I think
lots
I
of
think
ideas.
I will also read something so that I will be better prepared for the upcoming stuff which we're going to discuss. Yeah.
No, no. Now what we can do, Dinesh, right? We can have our extra session. Now I think I'm in at least good situation
Sure.
that.
Also, you are. Yeah, I don't want you to like.
Yeah.
So we will stop recording. It's exact 2 hours now. Okay, just
Okay,
stop
okay.
recording.
I'll just stop recording. Yeah. Yes,
Just
yes.
say something and stop. I don't know.
Yeah.
Okay.
Okay. So yeah, we'll meet in the next session on which is that date?
Next Tuesday.
Tuesday. Yeah, next Tuesday. Okay. So I'll let me stop recording.
Wait.
Yeah. Yes. Yes.